Hi again, dear students. This is Tamás Jávor. Welcome back to Rubber Duck Physics. Equilibrium might sound like a complicated physics term, but it's actually something you experience every day. Think of it this way. If you are lying comfortably on your couch, nothing is moving, no sliding off, no tipping over, you are in equilibrium. And that's exactly what we are going to figure out today, how we can describe that balance in physics terms. Now, equilibrium can apply both to objects that are at rest or objects that are moving with a constant velocity / constant angular velocity. But for today, we are mostly going to talk about stationary objects, those not moving at all, since their description is much simpler and all the physics that is interesting to us can be shown on them. Let's start with translational equilibrium, not moving in a straight line. This concept comes straight from Newton's first law, which is already familiar to you. An object will stay at rest or keep moving at a constant velocity unless acted on by an unbalanced force. If there is no net force on an object, we say it is in translational equilibrium. Here is the formula. Sum F equals 0, where forces have to be added up as vectors. If not all forces act in parallel lines, forces must be broken down to and added as components. But you already know this, right? This just means that all the forces acting on the object cancel each other out, so the object doesn't move. Think about a duck lying on a table. Gravitational force pulls the duck down, but the table pushes it up with an equal normal contact force. Then I start pushing it from the left, but static friction acts with an equal and opposite force to the right. Since these forces are balanced, the duck doesn't move. That's translational equilibrium. As said before, even though translational equilibrium applies also to objects moving at constant velocity, we are focusing on stationary objects for now. Next, let's talk about rotational equilibrium. Just like translational equilibrium deals with forces, rotational equilibrium deals with torques, the turning effects of forces. In rotational equilibrium, the object doesn't rotate. This must mean that the net torque acting on the object is 0, and nothing is making it turn. Here is the formula for rotational equilibrium. Sigma tau equals 0. The sum of all torques is 0. This means all the torques on the object cancel out. But be careful. Clockwise torques and anti-clockwise or counterclockwise torques must be added with their appropriate signs. As we have learned with all rotational quantities, clockwise torques are treated as negative and anti-clockwise torques are treated as positive. Staying at the level of the DP physics syllabus, we do not start considering torques as vectors, but I will sometimes put this plus-minus sign here in an index to emphasize that torques have a clockwise or counterclockwise direction, or to express that it can't freely be any direction. Sometimes it is called clockwise and anti-clockwise sense, and that's how the addition has to be computed. Let's see a seesaw example. If the kids on both sides of the seesaw weigh the same and sit at equal distances from the pivot, the seesaw stays balanced. That's rotational equilibrium. No rotation, no tilting. However, like we said in the previous video about torque, the seesaw isn't the best example for rotational motion, because it only moves through a small range of angles. But for building the concept of rotational equilibrium, where everything is balanced and stationary, it works well for us. At least in this video. Let's take a closer look at rotational equilibrium using a beam balanced on a pivot at its center. We'll place two weights on either side. When their torques cancel each other out, the beam stays level. This is rotational equilibrium. It's all about balancing the forces and torques so that nothing tilts or rotates. When the beam stays at rest, if it doesn't start to rotate as we release it, we know we have hit rotational equilibrium. So far, we have talked about translational equilibrium, where no net force is acting, and rotational equilibrium, where no net torque is acting. For an object to be in complete equilibrium, both must be true. Translational equilibrium, the object isn't moving away from where it is. For the current discussion, we have restricted it to cases where it doesn't even move in a straight line at a steady velocity. And rotational equilibrium, the object isn't rotating. For the current discussion, we have restricted it to cases where it doesn't even rotate at a steady angular velocity. Think about a ladder leaning against a wall. For the ladder to stay perfectly still, both the forces acting on it and the torques must balance. If they don't, the ladder might slide or tip over. Remember this example, we will return to it in a later video. Let's solve a simple equilibrium problem. You have got a 2-meter beam balanced on a pivot. At one end, you have got a 5 kilogram weight, and at the other end, you have got a 3 kilogram weight. The beam is light enough that we can neglect its own weight compared to the weights placed on it. The beam should be balanced. We need to figure out where to place the 3 kilogram weight to keep everything in rotational equilibrium. Remember, we need the torques to balance. The torque from the 5 kilogram weight is easy to calculate, it's just the force, which is its weight, times the distance from the pivot. Now we set up an equation to balance the torques and solve for the position of the 3 kilogram weight. Force on the left is 50 newtons, torque is 50 times 1 newton meter, force on the right is 30 newtons, torque is 30 times an unknown distance, newton meters. What is the sense of these torques? The weight pushing or pulling downwards on the left will turn the beam counterclockwise, therefore exerts a positive torque. When we said in the previous video that the direction of the force and where it is applied determine whether torque is positive or negative, this was what we meant. I hope it's clear now that it is this simple. Similarly, the weight pushing or pulling downwards on the right will turn the beam clockwise. It exerts a negative torque. 50 newton meters minus 30 newtons times d meters equals 0. If we rearrange, we get d equals 50 newton meters over 30 meters. That is 1.67 meters. That's where we have to place our 3 kilogram weight. Yeah, balance achieved. As usual, let me leave you with a question to think till you start the next video. Imagine you have got the same beam balanced on a pivot. But what happens if you move one of the weights closer to the pivot? Will the beam stay balanced or will it tip? In our next video, we'll explore what happens when torques aren't balanced, and we'll introduce the rotational equivalent of Newton's second law, the relationship between torque and angular acceleration. Today we have learned that equilibrium is all about balance, whether it is translational equilibrium where no net force is acting, or rotational equilibrium where no net torque is acting. And for complete equilibrium, both need to be true. But remember, in a broader sense, just because something is moving or spinning doesn't mean it's not in equilibrium automatically. Stay tuned for the next video where we'll dive into what happens when things aren't perfectly balanced and how torque leads to changes in rotational motion. At the end, let me add that I'm also available for tutoring you online, whether in DP Physics or in other similar curricula such as A-level Physics and Mathematics by any of the exam boards and AP Physics. Find my email address at the description of the Rubber Duck Physics YouTube channel viewed in your web browser, not your smartphone application, and feel free to contact me for tutoring lessons. Thank you for watching the video and see you next time.